Okay, you're going.
Okay, so we're starting with number 5 in the group problems. It's one that compares independent assortment to linkage. A asks, suppose a cell is genotype heterozygous for both, and assume that they are on separate chromosomes. Then asks what the genotypes of the gametes produced by this cell are and the frequency of each. So since they're all on separate homologous chromosomes, it's just a fourth for each category. So you have both dominant, dominant A, recessive B, both recessive, and dominant B, recessive A. And each of those are 1/4 for the frequency. B asks the same question, but it's saying that the dominant A is linked to dominant B and vice versa with the recessive alleles. And since the dominant and recessive alleles are linked, they follow each other in pairs. So 1/2 is going to be both dominant and 1/2 is both recessive. C is the same question, but it's asking about crossing over. So with crossing over, all of the possibilities can occur, just not at the same ratios. So for C, I have the same 4 as the first one. So it's the dominant, both recessive, and then the two non-parental, the recombinant ones, are the dominant A, recessive B, recessive A, and dominant B. And then D, it gives us the map distance. So it's 7.8 between the A and the B alleles. And because it's a crossing over, the two recombinant aren't going to be a large percentage or proportion of the offspring. And 7.8 is the number. So the two recombinants are going to be 7.8%. And the two parental, the both dominant and both recessive, are each 42.2%. Because that's the difference between 7.8 plus 7.8, and then you subtract 100 and divide by 2.
Okay.
So I'm doing number 1, and number 1 is Crystal and Margaret Green studied the relationship between 3 linked genes affecting coat color in mice. The 3 recessive genes are mahogany, agate, and ragged. The wild type versions are dominant ones. The scientists carried out crosses between mice that are heterozygous for all 3 genes and mice that are homozygous for all 3 genes, and they came out with these following results that we found in question 1. So the first part determined the allele arrangement in the heterozygous parent, and for that one we chose both of the ones that have the most number of offspring. So that would be a gout, wild type and mahogany, and then wild type, ragged, wild type. And so we come up with this part right here, this part right here, and then that's our heterozygous parents. And then we had to determine the gene order, and so by doing that, we found the double crossover. There we go. Of both, which is the 2 that are have the least number of offspring, and that ended up being a gout, ragged wild type, and wild type mahogany. And then to do that, we take our heterozygous gene, heterozygous parent, and we try to move it around the alleles to match it up to the hetero to the double crossover offspring, and then we ended up with the gene order wild type, A, and then mahogany, and then ragged wild type on the bottom. So we ended up with that. And then for C, we're to find the distance between them, and C is right here. And in that we found the single crossovers, and then we added up the single crossover, wild type, and ragged, gout, and mahogany with the double crossovers, and then we divided it by 206, which is the total number of offspring, and then multiplied that by 10, and we got 17.5. And then we did it again, but this time with wild type. I got wild type and ragged wild type mahogany, and so we added that up again with the double crossovers, divided that by 206, times that by 100 to get 13.1. And so the distance ended up being the dominant, so the wild type of ragged, is 17.5 mu from A, and then A from 13.1 to mahogany. And then to find out the interference, we then took those frequencies, and that's right here. We took those frequencies and we divided them by 100 and multiplied them together. So 17.5 divided by 100 and 13.1 divided by 100, and then multiplied them together to get 0.0229. And then we multiplied the 0.0229 by the total number of offspring, which is 206, to get 4.71. And then we took the equation that was given to us and did 1 subtract the total number of double crossovers, so 2, and then divide that by 4.71, and we got 57.6%. Oh, yeah.
So I have number 2. And in my work, I just wrote it all out because I don't like looking back at this page. So for the gene arrangement, we chose the 2 offspring with the most common genotype. And that was 314 and then 208, which was skewed, or the normal, with sable, and then vermilion, and then skewed with normal and normal. And then for B, the gene order, just did the crossover, the double crossover part, where I switched the SC with the S, and then had it normally, and then switched the V with the S on the other one, and then doing the double crossover squiggle that you showed us. I figured out that the gene order is sable with normal and vermilion, and then normal with skewed and normal again. And then the linkage map. I did the 2 least dominant ones, or the ones with the least amount of offspring with genotypes, and that was 10 and 14, which is the same as I did for B to figure those out. And then to figure out the other 2 that I should use, I circled the S and the SC and the V plus. And I got 150 for that one. And then to do the other one, I went the other way. So S plus, and then SC plus and V. And then I got 156 of those. And then I added those together, divide them by 1,000, which is the total number of offspring. And then multiplied them by 100, and then I got 33 MU. And that's the difference between the bristles and the body's alleles. And then the distance between the bodies and the eyes for the alleles, I did also the two least amount for the ones that have done the double crossover already. And then I did it the opposite way, so I did V plus and then SC plus and S, which are there are 30 of those, and then I switch sides, then it's V, SC, S plus. There are 46 of those, and then I added those together, divided them by 1,000, multiplied them by 100, and I got 10 MU. So here is the linkage map right here. And then for E, for the interference, I did 33 using the equation, 33 over 100 times 10 over 100, and I got 0.033, and then I multiplied that by the amount of offspring to get the expected number that we're supposed to get. So the expected number is 33, and the actual number was 24 that we got. And then do 1 minus 24 divided by 33, and I got 0.273 or 27% interference.
Okay.
So
So I did number 3,
and
and
this one was a little
this one was a little tricky because two of the were not represented in the offspring, and so we had to take that into account. So to find the heterozygous parent, you find the two most numerous, which was cold body at 484, and the glassy-eyed striped thorax at 441. So your the heterozygous parent's genotype is wild type eyes, a cold body, and wild type thorax, and then over the glassy eyes, a normal body and or wild type body, and a striped thorax. So to find the gene order, we write down all the possibilities, and then find the one that will give us the double crossovers, which are the least numerous. So I got wild type eye, wild type thorax, and then for C, to make the linkage map, we have to add together the double crossovers, so it's 0 plus 0, and then we do the single cross for the G, so that would be the striped thorax, which is 11, and the glassy eyes cold body, which is 8. So you add those together and divide it by 1,000, multiply it by 100, and it's 1.9 MU. And then for the other single crossover, you do 0 plus 0 for the double crossover, and then you do the wild type for all 3 traits, which is 27, and the glassy eyes cold body striped thorax, which is 29. Add those together, divide it by 1,000, multiply it by 100, which is 5.6 MU. So your linkage map looks like that. And then for D, we do 5.9 divided by 100 times 1.9 divided by 100, which gives us 0.001121. Multiply that by 1,000, you get 1.121. And then when you're looking for the interference value, you have 0 divided by 1.121, so that equals 0. So we know that 0% of the expected offspring occurred.
All right. For number 4, talking about.
I think you're muted.
We can at least do the B.
Sorry.
All right. For number 4, we are talking about corn in a corn maze. So step 1, we set up the homozygous or heterozygous cross with a homozygous recessive. Step 2, we find that 385 is the biggest, so that's our parent offspring, and then the 379 is the other one, so those are the two ones. We put the 385 on top, which is A recessive B wild type F, or sorry, the top 385 is recessive A wild type B wild type F, and then the bottom is wild type A recessive B recessive F. So step 3, we can see the ones that made a 2 and a 3 are wild type A recessive B wild type F for the 2, and then the 3 is wild type B wild type F recessive A. And from comparing those two genes, we can see that the F is what switched between them, or is what's different between them. So the A and the B genes are the ones that do the double crossover. So that lets us know our order is A, B, F. So step 4, we rewrite that, and then we switch the A's, and this leads us to finding that, and then we find the number associated with that. So that when we switch the A's, there's all recessive on one end and all dominant on the other. So we can take those, and those numbers, those genotypes correspond to the numbers 87 for all recessive and 98 for all dominant, and then we add them to the double crossover numbers. So we take 87 plus 98 plus 2 plus 3 is 190. Then we take our 190 and divide it by the total population of 1,000 and times it by 100, which gives us 19 MU. And then for step 6, we switch the B, pretty much do the same thing. And so that leads us to a genotype of one of them. The top one would be wild type A, recessive F, wild type B, and the bottom one would be recessive A, wild type F, recessive B. And the numbers that correspond with those are 26 and 20. So we take 26 plus 20 plus our double crossover, which is 2 and 3. So 26 plus 20 plus 2 plus 3 is 51. So 51 divided by 1,000 times 100 equals 5.1, which leads us to our map down here, where you have the distance between A and F is 19, and the distance between F and B is 5.1. To do step 8, we take that 19 divided by 100 and times it by 5.1 divided by 100, which gives us a small number of 9.69 times 10 to the negative third. We times that number by our total population to get 9.69, and that's what we would expect to get this. That's our expected outcome of how many double crossovers we'd have. So we take our actual and divide it by that number, and then we do 1 minus our actual divided by the observed, which gives us our I value of 0.484, or 48.4%, which is a good number, and that's what D is equal to 48.4%.